Hello Math Study students and welcome to another online lesson. Today we're starting a new unit on sets. Most of this unit will be review, things that you've seen either in this class or in previous classes. This video will be entirely terms and notation. I'll do a couple little examples along the way, but we're just defining terms basically. So in today's learning intentions, we're going to be talking about defining special number sets, as well as their abbreviations, and then identifying key terms and notation dealing with the study of sets, which is what we're talking about here. So you may want to print off this slideshow and just put that straight in your notes. That might be easier. Otherwise, you're going to be pausing the video a lot to write some things down, which is also just fine. Sets. A set is a collection of numbers or objects. We've seen set notation back when we studied probability, and some of these things will look familiar from the unit on probability. The number or objects in a set is called its members or elements. So you can have elements of a set or the members that are in a set. We use braces to represent a set. That's set notation. They're used to enclose the set, and commas separate the elements or the members. Sets are usually referred to with capital letters. So taking these first four bullet points and putting them all together, we could have V be our set. It's capital letter. If V is the set of all vowels, then set V is equal to, and then we've got this set here. And again, that's being used with set notation. Braces on either end, and we've got A, comma E, comma I, comma O, comma U, all the members of the sets, or all of the elements of the set, being the A, E, I, O, and U. The set name being the capital letter V, and it's just a collection of numbers or objects in this case. If I want to talk about things that are part of the set, I could say that A is an element of set V. I could also say that P is not an element of set V, and that's what we use right here, these Greek symbols. So this one, the one that looks kind of like an E, it's not an E, it's a Greek letter, but you can think of it as an E standing for element, and then again the slash through it means not an element of that set. I've got another example here. So we have set A. It contains the whole numbers 1, 2, 3, 4, 5, 6, and 7. We can again say that 4 is an element of A. 9 is not an element of A because 9 is not in this set, but 4 was. Something called an empty set. Empty set is a set with nothing in it. So we use either this symbol, which kind of looks like an O with a slash through it, or a 0 with a slash through it, or just two braces with nothing in it. That's, again, empty set, no elements in there. Part of our learning intention, I said we'd talk about special number sets. These are some of the special number sets. These are the ones that IB wants you to know. When you've got this fancy looking N, that stands for natural numbers, sometimes called counting numbers. Now, outside of the world of IB, I always see natural numbers and counting numbers included together, but usually 0 is not part of that. But for our class, we are defining natural numbers, including the 0. There's a set that I'm familiar with called the whole numbers, which is referred to with a W, and that would include the 0 and doesn't. But so if you've seen that in another class, I don't want to say you can forget about it or anything like that. Most likely most classes you take in the future, but unfortunately IB has defined it as natural numbers 0, 1, 2, 3, 4, 5, 6, on and on. Z stands for integers. It's a German word for numbers that begins with Z, and that's where the Z comes from. And that is all of natural numbers and their opposite. Well, 0 has no opposite, or its opposite is itself. And then you take a number like 1 and its opposite, which is -1, and then 2 and its opposite, which is -2, so on and so forth. So no fraction still, but it does include negative numbers. Now, if you put Z with a positive symbol at the end, that's what I've often referred to as the natural numbers, though it's not what's referred to here as natural numbers, and that is the positive integers. And then Z with a negative is going to be our negative integers. Neither of those include 0, because 0 is neutral, neither positive nor negative. The fancy Q is rational. Q standing for quotient, quotient meaning division, division being a way to write a fraction. So anytime you can write a number as a division of two things, like for example, 1/2 is certainly a rational number because I can write it as 1 divided by 2. 4 is a rational number because I can write it as 4 divided by 1. 0.3 repeating is a rational number because I can write it as 1 over 3, so on and so forth. Rational numbers. Now we're talking about fractions, decimals. Pretty much any decimal, if it repeats or if it terminates, meaning it doesn't go on forever, can be written as a fraction. Decimals that have no repetition but also never terminate, meaning never end, like pi, for example, 3.14, on and on and on, that has no pattern to it, that would be not rational. Can't write it as a fraction. R stands for real numbers. Real numbers are any number you can put on a number line. So let's think about numbers. Like, so let's say I've got 1. That certainly can go on a number line. 1/2, that goes on a number line. 0.3 repeating, that goes on a number line. What about a square root of 2? Well, if we throw a square root of 2 into a calculator, what do we get? 1.41 or something like that. So that would be right here. I can put that number on a number line as well. What about a number like pi? Well, that's a little bigger than 3, so there's 2, there's 3, and so pi would be right around here. That goes on a number line. Real numbers are pretty much every number you've studied, except for possibly if you took Algebra 2, you might have studied the imaginary number I, which is the square root of -1, which is not part of this class and can't go on a number line and is not real. We're only talking about real numbers. Real with a plus after it is all real numbers that are greater than 0. Real with a negative after it is all negative real numbers. Next class, we'll make a Venn diagram relating some of these things together. I think this is our last set of terms. Talking about elements of a set. The number of elements of a set, we saw this in our probability chapter. You put an n in front of the set name, and so the number of terms in set A would be abbreviated this way. So let's say A was set 1, 2, 3. Then the number of terms in set A equals 3 because there were 3 numbers in there. A set which has a finite number of elements is called a finite set. Now, what does finite mean? It's the opposite of infinite, in being a prefix that means opposite of or not. So this is infinite means never ending. Finite means it ends. Set A that I just made up here is a finite set because it goes 1, 2, 3, and then it stops. Infinite sets are numbers which have infinitely many, or sets which have infinitely many elements. We just looked at the set, for example, R, real numbers. That is an infinite set because you can have infinitely many real numbers. Really, all the sets that we saw there, even the integers and the natural numbers, even though the natural number starts at 0, you can keep counting up 1, 2, 3, 4, 5, 6, 7, 8, adding on new numbers forever and ever. Infinite sets. Suppose P and Q are 2 sets. P is a subset of Q if every element of P is also an element of Q. And we write this subset notation. Sort of looks like our or symbol from probability, but turned on its side with half of an equal sign below it. So P is a subset of Q is how we would read that right there. And so if this, for example, was P, 2, 3, 5, and this was Q, we can see that the 2, the 3, and the 5 were all members of Q. So P is a subset of Q, meaning it's contained within that set. Now you can also have sets that are identical and they are considered subsets as well. Like let's say I said set A was set 1, 2, 3, as I defined earlier. And then I said that is a subset of set B, which is 1, 2, 3. Oops, wrong brackets there, but 1, 2, 3, are those contained in both A and B? Yes, then A is a subset of B. B would also technically be a subset of A. But then there's something known as a proper subset where we don't put the line underneath. This is actually more common. And it's a proper subset if all the elements of one set are part of the other, but they're not equal. This one right here, this first example on the slide with the 2, 3, 5 being a subset of 1, 2, 3, 4, 5, 6. P is also a proper subset of Q there because they are not identical sets. However, these over here are not proper subsets because they're identical sets. Last bit of terms. And we've seen this before. We've got our intersection symbol. It means the same thing that we saw in probability. It means both P and Q. So let's say I have set P, which equals, I'm sorry, wrong symbol again, 1, 2, 3. And then I have set Q, which equals, let's go with 2, 3, 4 to keep things simple. So then the set P intersects Q would be equal to all the things that are in both of those. What's in both of those? Well, they both have a 2 and a 3. So that would be the set 2, 3. Worst 3 I've ever made. All right. Now, we've also got the OR symbol, or as it's referred to here, it's the union symbol. So going back to these same sets here, P and Q, if I want to do P, the set P union Q, that's anything that's in P or Q. So what numbers are in P or Q? Well, there's a 1 that's contained in P or Q. Just P, but it's in one or the other. We know the 2 and the 3 are in both of them, so that's certainly in one or the other. And then we have the 4. Again, we're using OR inclusively, meaning it could be one, the other, or both. So the OR includes more numbers. Last but not least, we talked about these words in probability as well. Two sets are disjoint or mutually exclusive if they have no elements in common. So if set P was right here with 1, 2, 3, and then set R was, let's say, 7, 8, and 11, those two sets, P and R, would be disjoint or mutually exclusive because they have no elements in common. So that's some vocabulary. Now the practice, I think, is going to be pretty straightforward. I even put 9 problems on here, which is more than I normally do, but that's on page 214. If nothing else, take just a peek at those problems and see if you can do some of those. But these terms should help you out with that. Until next time.